There's a few definitions of acids and bases. The Bronsted-Lowry definition requires that we look at where the protons are going. If we look at our first reagent, HCl, and we follow it to the other side of the equation, we can see that it loses a proton. So HCl is a proton donor. Water, on the other hand, as we go to the right side of the equation, we can see we're adding a proton there, so it's accepting protons. That means water is acting as our base. The other definition, which you see here is the Lewis definition, looks at electrons. You can see that water is donating electrons to acquire the proton from HCl. So water is our electron pair donor, and HCl then must be the receiver of electrons. Depending on the situation, it might be easier to watch where the protons go, or maybe sometimes the electrons. Let's go ahead and try to label these as acids and bases. For our first one, we can see that ammonia on the left side, NH3, turns into NH4 on the right side of the equation. So we're adding a proton. So this is a proton acceptor, which means ammonia is acting as our base. HCl, on the other hand, loses a proton. And so on the right side of the equation, you can see Cl- is there. So that is our acid. And don't forget, all bases on the other side of the equation are conjugate acids, and all acids react to form conjugate bases. And we know this because, in fact, these reactions are in equilibria. If we consider the reverse reaction, where Cl- reacted with NH4+, NH4+ would be the acid, and Cl- would be the base. In our second reaction, we have bicarbonate reacting with hydroxide. So again, we'll just look over on the right side of the equation and see what happened. Looks like bicarbonate was our acid, and hydroxide was our base. That gives us carbonate as our conjugate base, and water as our conjugate acid. In our third example, we can see the alkene is adding a proton to its structure, and so that's our base. Phosphoric acid is our acid, and then we have conjugate acid, conjugate base. You'll notice that I've been saying proton and not hydrogen for good reason. Let's look at our acid HCl here in this electron diagram. Our hydrogen is partial positive because oxygen is pulling electrons towards itself, which makes it partial negative. On water, we have oxygen, which has a couple lone pairs of electrons. We know that makes that partial negatively charged, and so we have an attraction between two atoms that have opposite partial charges. And what occurs is that a lone pair of electrons overlaps with the hydrogen atom right here. And as it does that, it gives that hydrogen atom 4 electrons, as it already had to in the sigma bond. And so we have to break one of these bonds. That's the only one we can break. And the electrons stay on the chlorine atom. So when we talk about that first arrow is overlapping with the hydrogen atom, only the proton is being abstracted. Both of the electrons in the sigma bond are actually going to stay on the chlorine atom. If we look on the right side of the equation, we can now see water has a third bond to another hydrogen atom. That gives it a positive charge. And chlorine has a fourth lone pair on it, which gives it a negative charge. Let's take a look at the reverse reaction. Here our base is chloride and our acid is the H3O+ molecule. That's hydronium. Now, understanding how this works is important. Our electrons on chloride are not going to be attracted to the oxygen atom. It is positively charged, but ultimately we don't want to give oxygen those 3 bonds. We definitely don't want to give it a 4th bond. What we want to do is give it its electrons back so that it has its second lone pair back, and that's this arrow I've just drawn there. When oxygen has a positive charge, as it does here, note that the 3 hydrogens it's attached to are electron deficient, and you can see that by looking at the blue coloration in the picture that's there. The equilibrium constant, KEQ, for a given reaction is defined as the concentration of the products divided by the concentration of the reactants. If we remove water from this reaction, given that it's generally in excess, so we treat it as a constant, we get a new equilibrium constant called Ka, which we defined as the acid dissociation constant. For strong acids that are very effective at donating their proton, the Kas are very large because the concentration of the products is very high in comparison to the concentration of the reactants. For a weak acid, where the forward reaction was not preferred, the concentration of the reactants is going to be larger than that for the products, and so we actually then have a very small Ka. Acid dissociation constants are expressed in scientific notation. For example, phenol has a Ka of 1.6 times 10 to the minus 10, whereas sulfuric acid has a Ka of 1.2 times 10 to the minus 2. The range of acid dissociation constants is really huge. And there's a new scale here, you'll notice, that's defined as the pKa. And that is defined by taking the negative logarithm of the Ka value. In this case, we tend to get a much nicer grouping of numbers that ranges, for example, between 0 and 50. Because of the mathematical function of taking the negative logarithm of the Ka, a large Ka results in having a small pKa. So therefore, strong acids will have small pKa's, and weak acids will have large pKa's. There's not a lot of acids that have negative pKa values, but you can see that because they are very small numbers, these are very, very strong acids. I'm sure you wouldn't be surprised to learn that HCl is a strong acid. And as we move up the scale here in pKa, we get to, for example, water. Water is not a very strong acid and therefore has a larger pKa value. Molecules that are strong acids, for example HCl, react to form weak conjugate bases. That would be Cl-. Conversely, molecules that are weak acids form strong conjugate bases. And this is important to know when we begin to think about how we can predict relative acidities or basicities of molecules. If we compare the structures of ethanol to tertiary butyl alcohol, you see that they differ only by a couple of carbon atoms. When these molecules react as acids, they donate the proton that's attached to the oxygen on each of these molecules to form the conjugate bases I have drawn on the right side. Now remember that all these reactions are in equilibrium. So if we create a molecule on the right side of the equation that's very stable, then the forward reaction is going to be relatively likely. If we form a product on the right side of the equation that's not very stable, then the forward reaction is not very likely. The information that I've got on this slide here tells us that a bigger molecule is less stable because the solvent has a difficult time solvating or stabilizing the anion that's formed. And so these are less stable, which means they're more reactive. And a more reactive molecule means it's stronger as a base. So this strong base correlates back to a weaker acid. In comparison, ethanol is smaller, and it's more easily solvated, and therefore it's more stable as an anion. That more stable molecule means it's a weaker base, and that translates back to a stronger acid. When we're considering how electron deficient a hydrogen atom is, what atom it's attached to makes a big difference. So in the upper left molecule, ammonia, we have a nitrogen here, and down below we have an oxygen. And oxygen is more electronegative than a hydrogen, and so naturally you would expect that the oxygen would be pulling electrons towards itself very strongly, and it does, and it pulls electrons out of these hydrogens, which makes them acidic and electron deficient. The nitrogen's also electronegative, but not as electronegative, and so these are partial positive also, maybe not so much. And if you consult the pKa table, you'll see that the pKa of water is around 16, and the pKa of ammonia is around 36. So it really makes a large impact, that atom directly attached to the hydrogens. On the structures on the right side here, we have fluorine atoms, and I know they're difficult to see, but they're attached to this carbon. So they're not directly attached to the hydrogen over here, but they're further down the line. And we still have an impact, and you can see that by the pKa values that are listed here. So fluorines are highly electronegative, so naturally they're going to pull electron density toward themselves. And the feeling is all the way through the molecule, and that term we use to describe that is the inductive effect. And so therefore we'd expect that the hydrogen on the bottom molecule is going to be more electron deficient than the one on the top molecule. And sure enough, it's reflected in the pKa value. Each of these three molecules have acidic hydrogens attached to oxygens. But you'll note that the pKa difference between the three molecules is pretty significant. And the reason boils down to the resonance stability of the conjugate base that each one of these molecules make. So let's draw a chemical reaction of these acids and see what kind of conjugate bases we would make. So ethanol reacts to form ethoxide. Phenol reacts to form phenoxide. And acetic acid reacts to form acetate. Now, one of the things I said a little bit earlier was that if the conjugate base that you make is very stable, then the forward reaction is quite favorable. If the conjugate base you make is unstable, then the forward reaction is not very likely. So by looking at the pKa values, we can identify that this is our strongest acid. And by that, we must be saying that the conjugate base is very stable. So there's something about this that is very stabilizing. Down here, we're admitting this is not a strong acid, and therefore our base is not very stabilized. And you might be able to see, indeed, the resonance stabilization that exists. But let's take a closer look. Let's consider the top molecule first. We've drawn this a few times in our class already. We've shown that the molecule can be drawn as a combination of Lewis structures. Let's draw one of them in here. So here's that structure, another lone pair right there. And the bottom side, let me draw that Lewis structure. Here's some arrows showing that redistribution of electron density. Okay. So on the top, we can see that there's a resonance structure we can draw which shows delocalization of charge. And you might remember we can continue to move this charge around the ring and show its delocalization and distribution among a few different carbons. But none of these are really as good as the first molecule because we have our negative charge on the more electronegative atom. So this is our more relative structure. So even though we can draw multiple resonance structures, we really only have one relative one. In the lower structure, the resonance structure we've drawn here is equivalently relevant to the one that's on the left side. And in this one, we can say both of these share that negative charge equally. So the minus charge is distributed between both oxygens. And because of that, we can say that the acetate molecule is much more stable a structure and less reactive. Remember, if something is less reactive and more stable, it makes it a weaker base. And that translates to the other side of the equation that tells us acetic acid is a fairly strong acid.